Okay, hello everyone, and welcome to today's webinar, Runtime Security Observability for AWS Fargate. In this webinar, we will show you the top challenges in securing AWS Fargate workloads, and most importantly, how to visualize, observe, and protect your Fargate workloads alongside your other cloud workloads with Deepfence. And with that, it is my pleasure to introduce today's speaker. Today we have Matt Krishak, Customer Success Architect from Deepfence, presenting today's webinar.
Thanks, Michelle. Good morning, good afternoon. Thanks everyone for joining our webinar on Runtime Security Observability for AWS Fargate. So before I get started, I just want to quickly introduce myself. So my name is Matt Krishak, and I help lead the pre-sales and customer success efforts here at Deepfence. So prior to joining Deepfence, I was a solutions architect at NGINX, which I'm sure many of you are familiar with. And I also spent time at a company called Volterra, where we focused on distributed Kubernetes and distributed edge cloud compute. Both of those companies were acquired by F5 Networks. So I've worked with some of the largest technology companies in the world, and I spent quite a bit of time helping DevOps teams focus on microservices deployments, digital transformation, and application layer security. So now that I'm here at Deepfence, I can continue to help organizations with their modernization efforts and kind of help drive home the importance of security in today's threat environment. All right, so here's a quick agenda of what we're going to talk about today. So I'll first talk about the top challenges securing Fargate deployments. I'll then talk about how we can deploy Deepfence on Fargate, and then we'll do a demo and showcase the visualizations, the observability, and the protection of not only your Fargate workloads, but your other cloud-native workloads as well. And then we'll wrap up with some Q&A. All right, so I'm going to show off my video just to save some bandwidth for anyone who's on a slower connection. All right, so let's talk about Fargate. So AWS Fargate is a serverless compute engine for containers that works on both Elastic Container Service and Elastic Kubernetes Service. So it's one of the most popular serverless platforms out there today. It is now used in nearly 1/3 of all container environments running in AWS. Fargate provides a compelling value proposition by letting the end user focus on building and deploying applications rather than provisioning, managing, and patching infrastructure. With Fargate, users only need to pay for the resources required to run their containers rather than over-provisioning and paying for the overhead of a full virtual machine. So while Fargate does offer improved security through workload isolation by running tasks and pods in their own runtime environment using dedicated resources, with the AWS shared responsibility model, securing services running within a Fargate instance from an application layer attacks is still the end user's responsibility, while AWS takes care of everything else. So in other words, let's say you have an Apache Struts container with known vulnerabilities and weaknesses. Those same vulnerabilities and weaknesses will exist no matter if the container is deployed on Fargate, an EC2 instance, or a Kubernetes node. Deploying on Fargate doesn't guarantee any additional level of security at the application layer, and this is the responsibility of the end user. So simply put, cloud provider solutions lack both the breadth and the depth needed to secure Fargate workloads effectively. So let's take a look at some of the top challenges securing Fargate deployments. So first one is no host access. So in a Fargate deployment, users do not have access to the underlying host infrastructure since the hosts are fully managed by AWS. While this increases productivity by simplifying the management of your container workloads, it also makes it more difficult to observe and secure your deployments. For Fargate pods running in EKS, lack of access to the Kubernetes APIs inside the container also makes securing the pod difficult since access to the Kubernetes API is critical to perform security tasks. So instrumentation. Containers running on Fargate do not have root privileges. So Fargate only allows unprivileged containers to run. This makes efficient and accurate runtime instrumentation of containerized applications a challenging task to complete. So without privileged access, it is possible to use the LD preload environment variable to direct the operating system to load a different version of the libc dynamic library that can intercept kernel system calls and record the calls and parameters. This method is very inefficient, but is not this method is very efficient, but is not very accurate. So many programs, for example, statically linked C programs or anything written in Go don't use the libc dynamic library and call the kernel directly instead. So LD preload will not be able to observe these types of programs. It's also very easy for highly motivated attackers to exploit and bypass LD preload completely, since it is a user level technique. An example of this would be, let's say, making system calls directly in assembly code. So ptrace is one of the most advanced system calls exported by the Linux kernel, and it makes it possible for a process with the right privileges to pause, introspect, modify, and control other processes. Many tools that are commonly used on a regular basis are based on ptrace, and AWS recently added Fargate support for ptrace in version 1.4. So ptrace is very accurate and is language and stack independent, since it directly intercepts kernel system calls and cannot be easily bypassed. However, it's not very efficient, right? And it requires high overhead, OS context switching, and it's not very fast. So think of this as the equivalent of setting a debugger breakpoint for every system call that is made. So no kernel instrumentation. So this approach consists of going down to the kernel level for efficient instrumentation, can be accomplished with traditional, but we'll call very invasive methods based on kernel modules, or with modern and less invasive methods like eBPF or extended Berkeley packet filtering. So kernel instrumentation is both efficient and accurate. It's efficient because collecting the actions in the kernel guarantees the lowest overhead, and it's accurate because the kernel never lies, right? But eBPF is one approach that eBPF is one approach that Deepfence will utilize when we're deployed on Linux distributions that support it. So, however, kernel instrumentation methods require root privileges and cannot be leveraged in Fargate deployments, unfortunately. So, code instrumentation. So instrumenting application code with language and framework specific SDKs is another popular approach that is used for tracing and telemetry collection. This approach is agnostic to the underlying infrastructure and works in Fargate, but it's intrusive as it requires code and CI/CD workflow changes. A variant of this is runtime bytecode instrumentation, which works for interpreted languages, but there's always a risk when instrumenting applications at runtime. So network observability. So efficient observation of network connections and inspection of network packets is a challenge in Fargate environments due to the lack of support for kernel level tracing mechanisms like eBPF, like we just mentioned. Right. So this forces security solutions to fall back on inefficient, less granular methods like VPC flow log inspection, which provides rudimentary information at best, or use inline proxies for TLS decryption and payload inspection that only increases, the complexity, causes performance degradation, and may even require modification to the application code to accommodate that particular proxy. So deployment model. The lack of host and privilege access breaks the standard model of deploying agents in Fargate deployments. Without access to the host, a single agent cannot observe other containers running on the Fargate host and thus breaks the one-to-many agent to container ratio. So to overcome this, there are alternate approaches to deploying agents on Fargate instances. So one method is to automatically download and install the agent in the application container when the entry point code is executed. So this approach, however, kind of violates that principle of container immutability. So another method is to modify the Docker file to add the agent during the CI/CD process. And while this approach does not violate that principle of container immutability, it is somewhat invasive and requires all container images to be rebuilt. So the least invasive method requiring minimal changes is to deploy the agent as a sidecar container, which can be mounted as a volume so that other running containers can access the agent and run the agent after container instantiation. So all three approaches have other issues and challenges, and each requires an application container to run a separate agent as opposed to one agent for all containers running on a single EC2 instance, thus increasing the overall overhead. All right, so those are the top security challenges when trying to secure Fargate deployments. All right, so now that we understand the top challenges here, let's go ahead and actually talk about how we can deploy Deepfence on Fargate. All right, so Before we can create a new task definition, right, there are a few prerequisites that will need to be completed that we won't be covering in detail in this particular webinar. So the first prerequisite, of course, is to deploy a Deepfence console running either on a small Kubernetes cluster or a single Docker host. So Deepfence is not a SaaS service. So this means that the console will be hosted entirely within your own infrastructure and can reside in any cloud or on-prem environment. It also means that any of the data that is transmitted between the Deepfence sensors that will be deployed in your infrastructure and the console is fully under your control and does not leave your environment, nor does Deepfence ever have access to any user data. So the next prerequisite then is to create an AWS secret that contains the user credentials needed to pull down the Deepfence sensor container image from our private registry. Once that secret is created, it can be linked to an IAM policy and added to an IAM role. You can also create secrets, of course, and policies for the other container images that are hosted in, say if you have your own private repositories, and they also need to be deployed as part of that Fargate task definition. And ultimately, the last prerequisite then is to create one or more IAM roles that contain the Amazon ECS task execution role policy, along with the policy that references the AWS secrets. All right, so now that we've talked about the prerequisites, let's actually go and create a task definition. So let me just switch things up here. I'm going to share a larger portion of my screen, and we'll actually go into the AWS console to do this. Actually, let me just quickly talk about what we need to do, right? So this slide outlines the high-level steps that we'll take to create a task definition that will deploy Deepfence along with your containerized applications. There are only a few additional steps required to add Deepfence to any task definition, and this really entails, adding the Deepfence sidecar container and adding a few environment variables to configure the Deepfence sensor. All right, so from the AWS console, we're going to go ahead and select a Fargate task definition. All right, so we're going to give this a name. So just for this example, I'm going to use Apache struts here. All right. And we're going to select the IAM roles that I had previously talked about. So in this case, I'd already previously set up a IAM role called Deepfence CS ECS task execution. So we'll go ahead and specify that. All right, I'm also going to specify the task execution role, right? And this is the one that would essentially be required to pull down the container images from a private repository. So I happen to add that secret to the same IAM role, but you could, of course, create two different roles for that. All right, so we're going to give this a resource size. So for this deployment, I'm going to choose 1 gig of memory and half a virtual CPU. All right, and this is where we then just need to add our container definitions. So I'm going to go ahead and start with the Deepfence sensor or the Deepfence agent. I'm going to call it Deepfence agent. All right, and then we're going to have to specify where we're going to be pulling this image from. So we're going to use this image name. And since this is coming from a private repository, I do need to do authentication there. And this is where I'm going to specify the ARN from that AWS secret that I previously created. So we'll go ahead and put that in. And then the last thing we really need to do here is just uncheck essential, right? Because once the task definition has been started, right, this sidecar container will exit. And if essential was still clicked here or checked, the entire task definition would be taken down because this one container stops running at a certain point. All right, so I'm going to go ahead and add that. Then we're going to go ahead and add our Apache struts container. So let me go ahead and name this Apache struts. All right, I'm going to go ahead and give the location of where this is being downloaded from. Now, because this is being pulled from ECR and it is a private repository, I don't need to check the private repository authentication, nor do I need to provide that any kind of AWS secret in order to do this. All right, so if I wanted to add health check information here, I could go ahead and add that in. So I'll just briefly do that. It isn't necessary, of course, for this particular deployment, but I'll do it anyways. And then really the next important thing, though, is we need to be able to specify the entry point and the command, right? So from an entry point perspective, we want to actually change the entry point of this container image to actually use the entry point of the sidecar container. And then what we'll do for the command is actually specify the original entry point of the application container itself, right? So both will get started. And this is basically instantiates the Deepfence sensor when this task definition starts. Now, the next thing we need to do is add a couple of environment variables to help configure this sensor. So I'm only going to focus on a couple of the key ones, but let's say, for example, one we need to add is Deepfence DF backend IP. This is actually the host name or the IP address of the management console that we have deployed. So we need to put that in. Notice here it is, I do have this hosted in GCP because we can host this essentially anywhere. All right, so the other one key environment variable is for DF file integrity on, and we want to say yes when we turn that on. And then the last really essential one is something called DF serverless, just to let the sensor know that this is an agentless, a serverless environment. All right, so then the only last thing that we need to do at this point then is to mount a volume from the Deepfence sensor sidecar, right? So we'll go ahead and name this, mount this in. This is not going to be read-only, right? So I don't want to check that. And that's pretty much it. That's it at this point. So one of the other things that we can do is that, there is support for sysptrace now in Fargate version 1.4. And if we add that capability in, there's something that we can do, which is do a memory dump of the processes within that particular task definition. All right, so I'm not going to go ahead and add this just because I already have it created. And then let's go ahead and launch that then. All right, so if I go back to the main service again. All right, so let's go ahead and launch a new task. All right. Oops. All right, so let's run this task. This is going to be for Fargate. I already have a VPC created for this and a security group already pre-selected. And it's going to auto assign an IP address for this. And then that's pretty much all we need to do. And this is very shortly going to go ahead and stand up. All right. So you'll notice here, I already do have a running Fargate deployment running. And while we wait for the other ones to come online, let's actually go to the management console to kind of help visualize and see what we're doing here. All right. So the screen that I'm currently showing is the Deepfence console, and it kind of represents that topology view of your infrastructure. So think of this as that 10,000-foot view of your infrastructure inventory, right? So Deepfence is really the only solution that can help visualize running Fargate deployments. Deepfence is the only solution that can help visualize running Fargate deployments, and not only can it visualize Fargate and other modalities like Kubernetes, virtual machines, and so forth. It can also see across multiple cloud boundaries, whether you're hosting in your infrastructure in AWS, Google Cloud, Azure, or even on-prem environments, right? So for example, here's my Fargate node that was already previously deployed. Here is a small 3-node Kubernetes cluster I have running in GKE. So you also notice here that Deepfence also can provide visualizations for your cloud native assets as well, right? So like, for example, such as an S3 bucket here, there could be a load balancer or even like a managed service like AWS RDS. On top of that, we also visualize an assortment of the most popular third-party endpoints like GitHub, GitLab, Cloudflare, and many others. And this really helps you better understand, who your applications are communicating with and how they're interacting with other services. So what I want to do now is kind of fast forward and actually run through our reverse web shell attack by exploiting some vulnerable code found in the Jakarta multi-part parser of the Apache struts container that I deployed in Fargate. So this is the same exploit that was used in the Equifax data breach, and it uses OGNL expression injection in the content type header value of an HTTP request to allow for remote commands to be executed. So in the middle terminal window here, or that you see on the screen, I'm I'm going to go ahead and use Netcat to listen on port 8000 on the client machine in order to receive that outbound reverse web shell connection from the Fargate container. So let me go ahead and start that up. And in the bottom window here, I'm going to go ahead and actually run that particular exploit. Now, while this is running, I actually have a Slack integration set up. Let me go ahead and show you that. Right. So basically, I've had this set up so that any alerts of critical or high severity will immediately alert and get outputted to a designated Slack channel, which is what we see here. So as we go into the alerts page then, right, we'll notice that we now have these alerts popping up. And this essentially what we're seeing here is information that's being passed through what we call the Deepfence correlation engine. So I'll talk about that a little bit more detail later. But let's start with that first HTTP request, right, containing those OGNL expressions injected into the content type header value. Right, so that's this one right here. Right. So one of the runtime signals that Deepfence is able to collect through the deployed sensors is off-host network anomaly detection, right? So Deepfence is able to do this through what we call our full out-of-band deep packet inspection from layers 3 to 7, including full TLS decryption without having to be a proxy or a man in the middle. And we do this while maintaining that perfect forward secrecy. So Deepfence is really the only vendor in this space with full deep packet inspection functionality. Other solutions out there either rely on, more the non-real-time log analysis, or they use proxies, which are really limited to that layer 7 inspection only. Or some of the solutions simply just don't provide network anomaly detection. All right, so if we take a closer look at the payload itself, right, because we are doing full deep packet inspection, we're able to see what was in that request. Right, if we look at the content type header value here, right, this isn't a typical content type header value, right? This is that OGNL expressions being injected into that header. So this type of level of visibility and detail, something you're just not going to be able to collect using cloud provider tools or other security platforms that rely on, things like AWS flow logs for inspection. Right, so at the bottom then of this alert page, we have a correlation chart, right? And the purpose of this chart is to show the potential correlation between the vulnerabilities and weaknesses and misconfigurations detected during vulnerability and compliance scanning, which I haven't talked about yet, but we'll circle back to, with the runtime signals that are being collected by the Deepfence sensors in real time. So the runtime signals are continuously fed through our Deepfence correlation engine, or it's combined with vulnerability and misconfiguration data using machine learning. So if we move from right to left on this particular chart, and we can see here that this attack was classified as web-specific apps, or an attack specifically targeting a web application like Apache Struts. And this anomaly was detected off-host through the network using deep packet inspection, and it was inbound from an external source that we've either not seen before or had a bad IP reputation, and was marked with high severity. So the list of the CVEs on the left side of the chart have been identified as having correlation to the events identified on the right side of the chart. So one of the CVEs that is listed is CVE 2017538, which you'll also happen to know or notice, right, is mentioned or is identified as part of the alert summary. So really, this is the correlation identification between the known vulnerabilities and weaknesses with the events that are happening at runtime. And this is being done through that Deepfence correlation engine. And this is really a key differentiator between Deepfence and other security platforms. So other solutions will show vulnerabilities and anomalous runtime behaviors as discrete events, but Deepfence is the only platform with the ability to correlate your known attack surface with runtime observability over both space and time to help you identify what's really going on in your infrastructure. So OGNL expression injection is a key indicator of an Apache Struts attack. So this particular attack vector was identified through rules-based detections. All right, so that's just one part of this potential exploit. Let's take a closer look at this file anomaly then. So the exploit that I ran also created a file called shell.bin in the temp directory. And not only was this file created, this file actually also contained executable code as well. This file anomaly was detected on the host through file integrity monitoring in real time using iNotify, since FA notify system calls require CAP sysadmin capabilities, which unfortunately are not available in Fargate deployments. All right, so you'll also notice then at the bottom of the correlation chart, we've also added that file anomaly to the correlation chart, again, helping keep track of the anomalous events as they're detected over both space and time, right? And continue to build out that picture. So the ability to kind of detect indicators of compromise like, file, process, and resource anomalies allows defense to not only observe and alert when potential zero-day attacks may be occurring, when an exploit itself has not been identified and thus can't be identified through something like a rules-based detection method. These indicators of compromise, typically are trails of evidence, of an exploit that could be potentially running within your, actively running within your environments. So defense gives you that complete runtime observability by being able to detect not only the known exploits through rules-based detection, but also zero-day exploits by looking for those indicators of compromise. All right, so now that we've kind of seen this live exploit in the runtime observability capabilities of the defense platform, the real question is, how do we do all this, right? So we'll take a couple of steps back. So moving on to the next slide, the defense platform, right? So the defense platform revolves around three core pillars to provide full lifecycle security, observability, and protection for your cloud native workloads. So now I like to use this acronym AIP to describe these pillars. So A stands for analyze, or being able to understand your known attack surface across your entire infrastructure. This not only entails being able to see what is in your infrastructure, whether it's a host, pod, or container, but also identify where vulnerabilities and weaknesses exist through vulnerability scanning, and where misconfigurations and proper settings could leave your infrastructure vulnerable to exploitation. Right. I stands for identify, or being able to recognize in real time when an attack or an exploit is occurring within your infrastructure, and being able to immediately notify an end user about this. This is runtime security observability that I basically just demonstrated in the previous demo. So P stands for protect, or being able to automatically safeguard your infrastructure when an attack or exploit has been detected. And this is really all about the runtime security protection. So these are the three fundamental pillars that defense focuses on to be a full lifecycle security, observability, and protection platform. All right, so if we take a closer look at the analyze part of AIP, or understanding what your known attack surface is, this really can be broken down into two distinct parts, right? The first part is being able to see across your entire infrastructure. And we touched on this previously when I showed the topology view in the defense console. As organizations expand, of course, beyond existing on-prem data centers and adopt hybrid and multi-cloud architectures, it can be difficult to maintain a sufficient level of visibility spread over those multiple cloud environments. And this will often lead to things like tool sprawl, with each cloud environment having its own specific set of tooling. Adding complexity really doesn't need to exist. So to solve the multi-cloud challenge, defense was built from the ground up to see across multiple cloud boundaries and work across multiple cloud modalities. So an example, you could be running a GKE cluster in Google Cloud. You could also be running virtual machines in Azure, virtual machines or bare metal servers in an on-prem environment, or be using serverless technologies like AWS Fargate, like I demonstrated today. So defense can not only see across all of these cloud boundaries, it also works across all the different types of cloud modalities like Kubernetes, virtual machines, bare metal, and serverless. So going back to the topology view then, so when this represents that, again, that 10,000 foot view of your inventory infrastructure. And this this information can be displayed in a variety of ways. Right. So the default view, of course, is by doing it by topology, by host. But we can also visualize this as Kubernetes clusters, containers, all the way down to the individual processes themselves. And we can do this in both a graph and table view. All right. So we're also able to view a little bit more detailed information about this as well. So for example, here, if I click on a particular node here, right now we're able to zoom in to this particular node, and actually, this could also be a pod, or it could also be a container, right? But we're able to get, detailed metadata about this particular host, right? So things about the operating system, the network interfaces that are there, any kind of private or public IP information, or if this is even hosted in a cloud provider, and which cloud provider is this being hosted in. So we can also view information about the resource availability, information about the inbound and outbound connections, running pods, if this is a Kubernetes environment, or the containers using container runtime. Again, all the way down to the individual processes that are running on this particular host pod or container, including the PIDs and the CPU memory utilization. So again, we can either go zoom out from that high level view all the way down into getting some very granular level information. All right, so let's talk about the control plane. So the Deepfence platform collects, maps, and visualizes this data by deploying a centralized console and a series of sensors across the environment where your workloads are going to be deployed. So the Deepfence console is a small, isolated 3-node Kubernetes cluster or a single Docker host, really depending on the size and scale of your infrastructure. So as I mentioned previously, Deepfence is not a SaaS solution, and the platform is hosted entirely within your own infrastructure. So at no time does data ever leave your control, nor does Deepfence ever have any access to user data. So the Deepfence sensors here, right, operate by initiating a bidirectional communications channel with the Deepfence console, and they automatically register with the console, which basically allows you to do things like automated zero-touch provisioning of the Deepfence sensors when you scale out and scale in your infrastructure. So the second part of analyze in that AIP acronym, right, is determine where your vulnerabilities and weaknesses exist, and the not only just the vulnerabilities and the weaknesses, but the misconfigurations as well. All right, so Deepfence pulls in threat intelligence feeds from 50 different sources, including the National Vulnerability Database, MITRE, Red Hat, GitHub, GitLab, just to name a few. So if we look at the vulnerability scan, so bring that up. So by default, Deepfence will scan for vulnerabilities and weaknesses in packages and dependencies within the base operating system. But we can also extend this to language-specific stacks like Java, JavaScript, Node.js, and Python. Scanning can be targeted at individual hosts across all hosts and pods in a Kubernetes cluster, or specific container images spanning the entire infrastructure. So the vulnerability scanning is run on the Deepfence console and not at the sensor to make sure that there are really no performance impacts within the workload infrastructure. Vulnerability scanning is also done intelligently. And what I mean by this is, Deepfence tracks where the container images have been deployed and which vulnerabilities exist in those container images. So that's not, that's only necessary to scan a particular container image once, as opposed to having to scan it at every single place that is deployed. So vulnerability scanning can be scheduled to occur on a regular basis, and the platform has a full REST API support to initiate the scanning throughout the various stages of your CI/CD pipeline. So whether that's before an image has been pushed to a container repository, at a container registry, or even at runtime, once a container is deployed, we can do the vulnerability scanning at all those different spots. And scanning is not just limited to container images, of course, right? It can also be run at the host level as well. All right, so moving on then. So as your infrastructure grows and the number of workloads increases, it's entirely possible that you could have hundreds, if not thousands, of unique vulnerabilities floating around in your infrastructure. So some of these vulnerabilities you can ignore, others can be fixed later. But their question really then becomes, how do I identify which vulnerabilities I should be most concerned about right this second or right now? So Deepfence provides this information in a most exploitable vulnerabilities list. Right. So think of this as, like a top 10 list of the most exploitable vulnerabilities that can hurt you the most right this second. So in this list of top vulnerabilities, you'll notice there's a score right here. This is a dynamic score that is calculated by Deepfence and takes into consideration not only that CVSS score provided by the threat intelligence feeds, but also the runtime signals being collected by the Deepfence sensors. This score is continuously readjusted based on the information provided by the runtime signals. Right. So while vulnerability scanning looks for the known CVEs and weaknesses, then compliance scanning is really all about identifying misconfigurations in your infrastructure, right? So Deepfence can run compliance scans for system hardening, and CIS, NIST for Kubernetes, and PCI DSS and HIPAA environments where it's applicable, and is one of the few platforms out there that can actually do compliance scanning of a running Fargate deployment. All right, so if we look at the compliance, then, for example, here's just a brief overview of the compliance scans, right? So from a controls perspective, right, we have the ability to go in and activate or deactivate certain controls, because not every single compliance scan will be necessarily applicable to your particular environment. And then, of course, this information can be output in a report summarizing the compliance scan results. All right, so the Deepfence platform was built with an API-first approach, and everything you've seen so far on the console has a corresponding REST API to it. So this makes it incredibly easy to integrate Deepfence into your existing CI/CD pipelines and development workflows to accomplish tasks like auto-initiated vulnerability scanning, compliance automation, and auto-generation of reports. Okay, so moving on then. So the I part of identifying AIP is all about being able to detect when attacks and exploits are occurring within your infrastructure in real time. And this is handled by the Deepfence runtime that uses those sensors deployed in your infrastructure. So the Deepfence sensors deployed across your infrastructure are designed to be lightweight, small, lightweight in terms of resource consumption, and they're also application agnostic. And then, really what I mean by that is we don't expect or want application developers to have to modify their code to accommodate Deepfence. So it's a self-contained binary that can be deployed in practically any environment and collects runtime signals across various sources to look for those indicators of compromise. So these sources are network, right? So for example, covering both the shallow and full out-of-band deep packet inspection from layers 3 through 7, including that TLS decryption, without having to be a proxy or man in the middle while maintaining that perfect forward secrecy. So the decryption and analysis of the network packets is completed out of band at the Deepfence console. And this is done not only to keep the Deepfence sensor footprint as small as possible, but also eliminate any obstructions in your application's fast data path. So typically proxy-based solutions are inline and they only add latency and complexity where it doesn't need to exist. And Deepfence is not a proxy-based solution. So the other sources that we look at are file integrity, process integrity, system call, and resource monitoring. And these really are the primary vectors through which an attack or exploit will try to infiltrate your infrastructure. So by inspecting the runtime signals in real time, Deepfence is not only able to identify known exploits through rules-based detection, but it can also detect zero-day-based attacks by looking for the indicators of compromise or those artifacts of an exploit. And this is really a key differentiator from an agent or sensorless solutions that depend on things like log analysis or snapshotting for detection. So agent or sensor-based solutions like Deepfence offer real-time detection versus delayed, inefficient, or even inaccurate detection by agentless or sensorless based solutions. So in non-Fargate deployments, right, the Deepfence sensors use eBPF or extended Berkeley packet filtering as part of the runtime detection. And eBPF is a modern approach to instrumentation. And by using eBPF, the sensor can reside in Linux user space while gaining all the advantages of being in Linux kernel space without having to be a kernel mod. So, hooks and probes are set in kernel space so that the Deepfence sensor has full visibility into the host and everything that's essentially running on top of it. The sensor can essentially see what goes in, what comes out, and what changes, that full complete observability. So the Deepfence sensors are designed to be easily installed and can work across many different types of infrastructure, including serverless ecosystems like our Fargate, like we demonstrated today. Or Fargate in other environments where access to the underlying host infrastructure is severely limited or completely blocked. So in a bare metal virtual machine or container runtime environment, the Deepfence sensor is typically deployed as a single container or a systemd binary on the host. In Kubernetes, the Deepfence sensor is deployed as a daemon set or just another pod that runs on each worker node. And then again, in those serverless environments like Fargate or those environments we do not have access to the underlying host infrastructure, the sensor is deployed as a sidecar container to those existing container workloads. And it still retains that same functionality as the other deployment methods. All right, so moving on to the last pillar of AIP, which is P for protect. This is all about the automated protection of your infrastructure when attacks and exploits have been detected. All right, so I'm actually going to do another demo of this, but in order to do that, I first want to help explain what these protection policies are, right? So Deepfence can apply two different methodologies when it comes to workload protection. So the first method, referred to as a quarantine policy, is really a modern approach built for cloud-native applications. It deals with applications directly instead of applying that traditional network-based security policy like cutting off network access or blocking bad actors. So in a Kubernetes environment, you can choose to delete a pod, right? Or in a container or runtime environment, you can either choose to stop, restart, or pause a running container. And this allows Deepfence to be laser focused on how it quarantines or expunges exploits that are active in your infrastructure. So I already have a policy set up. Let's go through and walk through what that would look like. So in this case, I want to have a policy that will activate when it detects an Apache Struts exploit, right? So I do know that there happens to be a high severity event, right? And the class type here, again, if you remember, was web-specific apps. And what I want to say is if I receive just one alert of that happening, I want to go ahead and delete my particular pod, right? So this is the policy that's running or that I have enabled. And let me go ahead and show my terminal window again. And let's go ahead and run this. So before I do that, I want to just show that I have 3 Kubernetes pods running for Apache Struts in my GKE environment, right? So you can see that. Let me go ahead and reset the exploit itself. And let me go ahead and then kick off the attack, right? So this is going to essentially give me shell access to one of those particular pods that are running. And while I do that, I want to run a couple of commands as well, just to showcase the process anomaly detection that we're able to do. And also kick off a core dump as well. So while that's running, actually, you can see that termination policy is immediately kicked in at this point, right? So we saw that the pod was terminated. Of course, Kubernetes recreated that pod because I needed a minimum of 3 pods running to meet the replicas, the number of replicas that I specified. And because of that, you also see here that my terminal connection was actually immediately terminated. And not only was it terminated, right, any of the kind of artifacts of that exploit that were a part of that attack, like say for that shell.bin file that was created, for example, right, all those have just immediately been expunged from the system at this point. All right, so we go back to the alerts real quick here. I just wanted to kind of also show the some of the process anomalies that were detected as well, right? So you can see here, for example, that strace command that I ran, that immediately showed up because that was making a system call to the kernel, and also that core dump that I forced, right? That immediately also showed up as well. And again, these are the indicators of compromise that really are being detected in that real-time fashion. All right, so the second method that Deepfence can use to protect your infrastructure is more of that traditional network-based approach, right? And this is really just all about blocking those bad actors, right? So from a criteria perspective, again, it's very similar to how we set up the quarantine policy. The only real difference here is that instead of acting on the application itself, right, we're simply going to block the bad actor's IP address for a user-specified amount of time or indefinitely. All right. All right, so this wraps up the demo portion of the webinar, and I just want to take a couple of moments then to kind of help summarize what I've talked about today. So there are dozens of products and open source projects that address the different aspects of security of your applications and how they're secured at runtime. Most of them are point solutions. They are very good at what they do, but it's really up to you to kind of piece together the information from each and build a bigger picture of what is actually going on in your infrastructure. And this is really where Deepfence is unique, right? It combines 2 types of solutions, that vulnerability and compliance scanning and that runtime security observability, and it integrates the 2 together, providing a correlation between your known attack surface with the runtime observability over both space and time. This allows Deepfence to give you much better informed insights into what's going on in your infrastructure and helps prioritize what to look for. So as an example of that, right, the vulnerability scanner might detect that a component in your application could be exploited by a local escalation attack. Someone would actually need local access to mount that attack. On the other hand, though, the vulnerability scanner might be able to detect that another component in your application stack is vulnerable to network attacks. So, something like Apache struts. It might determine that this application or component is at the edge of your infrastructure and processes traffic directly from the internet, where there's a much bigger risk for exploitation, as opposed to that, let's say, that local exploit. Deepfence builds a map of the vulnerabilities and scores them based on the risk, so you know what to prioritize. The runtime observability is where things get even a little bit more, even more clever, right? Deepfence can detect if someone has sent a known Apache struts exploit to a vulnerable component. It can detect when suspicious activities are happening on the application or in your infrastructure, such as a process anomaly or an unexpected file modification. And Deepfence puts all the signals together and alerts you if it identifies that an attack or exploit is occurring in real time. It can also quarantine, expunge, or block additional activity once an attack or an exploit has been identified. So Deepfence is a unique platform that gives you that full lifecycle security observability and protection across your entire infrastructure. All right. So thank you all for very much for joining today. It's been a pleasure, and I'll go and hand it over to you, Michelle, for some Q&A and wrap up.
Okay, great. Matt, thank you so much for walking us through the top challenges with traditional security methods for AWS Fargate. Also, thank you for showing us how to deploy Deepfence with Fargate Tasks, and most importantly, how to visualize, observe, and protect running Fargate tasks like your other cloud workloads with Deepfence. We are now in the Q&A portion of the webinar, so if you have a question that you would like to ask Matt or the broader Deepfence team, please use the Q&A box at the bottom of your Zoom window. And with that, I'll go ahead and get started with the questions that we have coming in. The first question, do you support other cloud providers in addition to AWS?
Absolutely, right. We support all the major cloud providers, including the we'll call the kind of the second and third tier level providers. Right. Deepfence was built again with the ground up to be able to work across any environment, any different cloud, and yeah, absolutely, we can work across those environments.
Okay, we've got another question here. How can I trial Deepfence?
Yeah, so for trial purposes, just simply get in touch with Deepfence. We do have an open source initiative that we're going to be coming up with here shortly. But really a lot of the features that I showcased today, like the deep packet inspection and that runtime protection, that is built into our enterprise edition. So please absolutely contact us and we'll be happy to set up a trial for you.
Okay, those are the only questions that I see in the Q&A box at this time. Any closing comments for us, Matt?
No, thank you very much, everyone, for joining. It's been an absolute pleasure to kind of share some of the knowledge that I have, and here the team here at Deepfence, and we definitely look forward to hearing back from some of you if you're interested in trialing Deepfence.
Okay, thank you everybody for joining today's webinar. We hope to see you at another Deepfence event in the future. Thank you.